So it's finally time to derive the forward current in the p-n junction. Deriving the forward current of the p-n junction is a daunting task. So what I'm going to do first is I'm going to discuss what the plan of action is, and then we'll move forward. The plan of action will be actually to find an expression for the distribution of excess holes in the n side. So we'll find an expression for delta p of x. We just want to know what this curve looks like. And we want to know what this curve looks like as well, the excess electrons on the p side. When we manage to get these excess holes and electrons, their profiles, we can find their gradients with respect to x, which allows us to find diffusion current that results from the injection of these minority carriers. And so then we will find the diffusion current that happens due to electrons diffusing, due to holes diffusing in this direction and electrons diffusing in this direction. We'll then talk about how these two diffusion currents are actually not the total current of the diode, but that by calculating them at the interface with the depletion region, we actually manage to find the total diode current. So first of all, we are going to start with the differential equations we obtained from the current continuity equation. So we have dp d2 dp delta p by dx2 is equal to delta p over tau for holes on the n side, and similarly dn d2 delta n by dx2 is equal to delta n divided by the lifetime of electrons on the p side. Now dp times tau pn has a unit of meter square. Similarly, dn times tau np has a unit of meter square. And so we're going to give these a name, and we're going to call this LP square, and we're going to call this Ln square. And what do they represent? What do LP and Ln represent? So they represent the average distance that an electron can survive on the p side, an excess electron can survive on the p side, and Lp represents the average distance that a hole can survive on the n side. So excess holes and excess electrons get quickly reabsorbed or recombined on the opposite side, but there's an average distance that they can survive while traveling. So this allows us to write the differential equations in a more friendly way. So we have d2 delta p by dx2 is equal to delta p over lp square, and d2 delta n by dx2 is equal to delta n over ln square. So both of these equations have a general solution which takes a well-known form. So delta p of x is then going to be c1 e to the power of x over lp plus c2 e to the power of minus x over lp. So this is the general solution of this second-order differential equation. c1 and c2 are constants, and we are going to need two boundary conditions in order to find these two constants c1 and c2. Now the first boundary condition is actually really easy to tell just by looking at the graph. We know that very deep in the neutral zone, p returns back to its equilibrium level. So very deep in the neutral zone, p is equal to p and naught, which means that delta p is equal to 0. So we know that delta p of infinity is pretty much going to be 0. So this is the first boundary condition that we can use. We need a second boundary condition because we have two constants, c1 and c2. But the second boundary condition is also easy because we already derived it using the excess minority carrier injection. So we dedicated a whole video to finding these values of excess minority carriers at the interfaces. And so we know that delta p of 0 is equal to this expression, which is p n naught times e to the power of q vf by kt. But notice that this is actually p, not delta p. So we have to subtract minus p n naught. So this is the other boundary condition, right? So basically delta p of 0 is equal to ni squared over nd into e to the power of qvf by kt minus 1. So exponentials keep showing up because the distribution of carriers across the energy levels has an exponential dependence due to the Fermi-Dirac function. Now, using these two boundary conditions, we can find an expression for delta px, which is the profile of excess holes on the n side, and delta p of x is going to be pn naught into e to the power of q v forward by kt minus 1 into e to the power of minus x minus xn divided by lp. And this is going to be valid for x greater than or equal xn. So basically this is the profile of excess holes beginning xn and moving forward, and it has an exponential dependence on x, and it drops from a maximum level at xn of delta px of 0, and it drops exponentially towards 0 at infinity, which is kind of what we can see from the graph to begin with. Similarly, we can find an expression for delta n of x, which is np naught into e to the power of qv forward by kt minus 1 into e to the power of x plus xp over ln. And this is going to be valid for x is less than or equal minus xp. And at minus xp, we have the maximum value, which is equal to this bracket. And as we go towards minus infinity, we get a value of 0. So these are the two boundary conditions we will use for the expression of n of x. Now we have expressions describing the graphs, these two curves describing the excess carrier levels on the n side and the p side, but we want to re-express these in terms of currents. So how do we get current expression from this? Like how can we use these to get currents? And the thing is, we know that hole diffusion current is equal to dp times q times dp by dx. We also know that electron diffusion current is equal to dn q dn by dx. And we also know that dp by dx is equal to d delta p by dx, because only delta p is a function of distance. P and naught is not a function of distance. Similarly, on the p side, we have dnq d delta n by dx. So now we can take the expressions of delta n of x and delta p of x and plug them into these two equations to find expressions for jp of x and jn of x. And as the x in these two expressions show, we will find that the diffusion current is a function of distance. And this is true because let's recall what jp is and what jn is. jp is the hole diffusion current as it enters the n zone. It is the holes, the excess holes that have been injected by diffusion from the p side. Jn is an electron current on the p side which has been injected from the n side. Because holes recombine quickly on the n side and electrons recombine quickly on the p side, we will find that jp is actually a function of x and jn is a function of x, and they both drop towards x equals infinity and x equals minus infinity, pretty much the same way delta p and delta n drop, because jp and jn are strong functions of delta p and delta n. And therefore, we will find that both diffusion currents are going to be functions of x. But actually, what we really care about is jp at xn and jn at minus xp. So these are the two currents that we care about. And if we calculate these two currents, we'll find that they are equal to q dp pn naught divided by lp into e to the power of q v forward by kt minus 1. And for jn of minus xp, it's going to be pretty similar, except we have q dn by ln times np naught into e to the power of q v final v forward by kt minus 1. So what are jp of xn and jn of minus xp? These are the diffusion currents for holes at the point xn and the diffusion current of electrons at the point minus xp. So these two expressions that we just found are the diffusion currents for holes just as they are entering the n zone, and for electrons just as they are entering the p zone. They are the maximum values of these two diffusion currents. But as we will see in the coming video, the summation of these two currents is actually the p-n junction current, and it is the p-n junction current everywhere. And so these two currents are really important. Even though we calculated the diffusion currents at very specific points, these points have a significance.